Hey students, welcome to the first lecture of Linear Algebra II in the G30 program of Nagoya University. Due to the special circumstances, I need to record these lectures here in my living room and we cannot do face-to-face lectures. So before I start, I want to make some general comments. So for this lecture, I will release some lecture notes. My handwritten notes I will use here. But in addition, I will also release some overview notes which contain all definitions and propositions for this lecture. And you can find both of them on my homepage. Okay, so in Linear Algebra II, what we want to do is we want to generalize a lot of things we did in Linear Algebra I. And the notion we want to introduce is the notion of the so-called vector space, which generalizes the Rn, which we studied in the first semester. But before we do this, I want to recall a little bit what we did in Linear Algebra I. So chapter number 0 is Review of Linear Algebra I and Motivation. So what did we do in Linear Algebra I? So the first thing we did, we solved linear systems, which were just a collection of linear equations. And then, after this, we introduced matrices and vectors to describe these linear systems. So, and what was a vector? A vector was an object like this, a tuple of numbers, x1 to xn, and this was an element in Rn. So these x1 to xn were real numbers. And a matrix was just a table. So A, if A is an m by n matrix, we denoted the space by this. And then a linear system was solving something like this, that A times a vector x equals some vector b, and this b in this case is in Rn. And for these vectors, we had some operations. So for example, if I had two vectors of size n, then what I could do is, so we had two operations. The first was addition. So I could add them. And this again gave a vector of size n. So for example, if I add the vector 1, 2 plus the vector 2, 3, just component-wise, we add these numbers. So this is 3 and this is 5. And the other operation we had were scalar multiplications. So what we could do is, if we have a real number lambda, we could multiply this with a vector x and again get a vector. So for example, if we take the number 2 and we multiply it with the vector 1, 2, this just meant that each entry we multiply with 2. So this is 2, 4. And then using these operations, we introduced some objects. So for example, the next thing we studied were linear maps. So linear maps. And what was a linear map? A linear map was a map or a function from Rn to Rm. And this map should satisfy two conditions. The first condition was that if I take the linear map of a sum like this, then this should be the linear map of the first entry plus the linear map applied to the second entry. So this had to do with this addition. And the second property had to do with the scalar multiplication. Namely, if I take the linear map of lambda times a vector, then this should be lambda times f of x. Okay, so after studying these linear maps, which were, for example, given by multiplication by matrices, we studied subspaces. So subspaces. So we considered a subset U of Rn, and this had three conditions. So U was a subset if it satisfies these three conditions. The first was that 0 is in U, and by 0 we meant this vector, this 0 vector, which just contains n zeros. And then if I have two elements in U, then we can add them, and the sum should also be in U. So the subset U needs to be closed under this addition, but it also needs to be closed under the scalar multiplication, meaning that if x is a vector in U and I have a real number lambda, then also lambda times x should be in U. And we gave a lot of examples. For example, if we are in R2, then lines through the origins were examples for subspaces. And other examples we studied were images and kernels of linear maps. So if I had a linear map from Rn to Rm, then the kernel was a subspace in Rn, and these were all vectors which get sent to the 0 vector in Rm. So here the kernel of f is inside here, and the image was a subspace on this side, and these were all vectors we could obtain by implying this map f to all elements in Rn. And then the last thing we discussed were linear independency and basis of Rn, and also of subspaces. And then we talked about the linear span, and the basis was a collection of vectors which were linearly independent and which spanned your space. So in here you see that in all these definitions we don't really care how these objects look like. We just use that there's some notion of addition and some notion of scalar multiplication to describe all these properties. And in real life, or in your life as a natural scientist, there are a lot of objects besides these vectors which also have some addition or scalar multiplication, for example polynomials or functions. And for these, all these objects or these notations also make sense, and they are really interesting. So what we want to do at the beginning of this course is to generalize these ideas to more general objects, and then study these specific notations. Okay, so let me give you one example of an object where we also have some addition and scalar multiplication, and where this notion of subset also makes sense, and the notion of basis and linearly independence. Okay, so this is example number 1. And for this, let f R to R denote the set of all functions from R to R. So for example, one example would be the exponential, e to the x, or the sine, the cosine, and all functions you can imagine. So this set is a really, really big set. And in this set, we can also define addition and scalar multiplication. So for example, if I have two functions in this set, f and g, then I can define f plus g, the function f plus g. So I need to say what this function is if I want to apply it to some x. And the definition is just I take f of x plus and then g of x. So this is the addition for functions. And also we have some scalar multiplications. Namely, I can denote So what I mean by lambda f, this new function evaluated at x, just means I multiply the number lambda with the value of f at x. So and this is for all x in R. So in this set of all functions from R to R, we also have addition and scalar multiplication. And now we want to consider a subset, which I will denote by U. And U is now all functions in this really big set which have the property that the second derivative equals the function itself. So what would be an example of a function in this space? So one trivial example is the zero function, so which I will denote by n. So n of x, the zero function, means that this is 0 for all x in R. So if I define a function like this, then we can see that this n is contained in this set. And also, if I have two elements in this set, for example, if f and g are in U, then it's also easy to see that f plus g is in U, because f plus g is just defined by adding f of x plus g of x. So if the second derivative of x, of f, equals f, and the second derivative of g equals g, then also the second derivative of this sum equals just this sum. So if I have two elements in this set, then also this function f plus g is in U. And similar, if I have f in U and lambda in U, a real number, then also this function lambda f is also in U. Because these just follow from the properties you learn in calculus for the derivative of a function. So you see this U satisfies these three conditions. So there's some zero function which corresponds to the zero vector, and we have addition. So this set U is closed under addition, and it's also closed under scalar multiplication. So from this we could say that that U is a subspace of this set FRR. But we didn't really define this notation in general yet, but somehow it's exactly the same conditions as we had in Linear Algebra 1. So how does this U actually look like? So here we have one example of a function which is in U, but there are probably more exciting examples which satisfy this condition. And one example is, of course, the exponential function. So I will call this f1. So f1 of x I define to be e to the x. So the derivative of this function is just e to the x, and then taking again the derivative is just e to the x. So this is one example in U. So f1 is in U. But there's also another example which looks similar. f2 of x, you could check that if I take e to the minus x, so if I take the derivative of this, then this is minus e to the minus x. And if I take again the derivative, I multiply again with the minus 1 and get again e to the minus x. So this is also an example of a function in U. And by these two properties, we see if we take a linear combination of these, then this is also an element in U. So we could say that this U, well, the first you need to say that actually one can show that these are the only examples in U. So we can show that actually U is the span of f1 and f2. And one can also show that these two functions are linearly independent, by which I mean that if this linear combination is a zero function, then these coefficients lambda 1 and lambda 2 need to be 0. So f1 and f2 are linearly independent. But also here, we didn't define this notion in general yet. But what we will see later, that's similar to linear algebra 1, this means that this subspace U has dimension 2. And f1 and f2 are a basis of this subspace. So U is a subspace of dimension 2 of this really, really big space F. Yes, and in the following we will now make sense of all these words for general objects and will define the notion of a vector space. Okay, so let's start with chapter 1, vector spaces. And we directly start with the definition. So definition 1.1, the definition of a vector space. And what we want to define is if we have a set and we have some addition and scalar multiplication such that they satisfy the same rules as we have for vectors, then we call this set a vector space. So more precisely, a vector space, or in our case, we will just consider something which is called the real vector space. So all the scalars will be real numbers, and you can even do it more general. But in our case, we just consider real vector spaces. So a vector space is a set V with two functions. And the first one is our addition. So we have a function where we can take two elements out of V and get again an element in V. So if I have a U and a V, I can make sense of U plus V. So this is the addition. And we also have some scalar multiplication, which means if we have a real number and an element in V, we can get a new element in V, and we denote it by lambda times V, or usually we just write lambda V. And these should satisfy certain rules, and these rules are exactly the rules you always use when you calculate with vectors. And so there are two categories of rules. So we have these two functions satisfying certain rules, and the first set of rules are properties for the addition, and I will denote them A1, A2, A3, and A4. And the first one is that if I have three elements in V, U, V, and W, then it doesn't matter if I first add U and V and then add W, or if I first add V and W and then U. And this is called associativity. So it doesn't matter which one you evaluate first, which is clear for vectors, but here it's one of the conditions for this new general plus. And the second condition is that if I have two elements in V, then the order how I add them doesn't matter, meaning that U plus V is the same as V plus U. And this is called commutativity. So meaning the addition is commutative and associative, which is true for the usual vector addition. And now there's the third condition is that there exists a special element such that if I add this element to some vector, this doesn't really do anything. So the statement is that there exists some element n such that for all vectors u in V, if I add this n plus u, then it doesn't do anything. This will just give u. And in the classical case, this n is just the zero vector. And one of the conditions is that for every vector space, there is such an element such that if I add it to any other element, it will not change this element. And the fourth condition for the addition is that for all elements u, I have the inverse, which means that there exists an element v, such that if I add this v to u, I will get this n. And for the usual addition of vectors, this means if I have a vector 1, 2, I can find another vector such that if I add this vector, I get the zero vector. And in the case 1, 2, of course, I can just take the vector minus 1, minus 2. And if I add it, I get this vector 0. So these are the conditions for addition. And there are also conditions for the interaction of addition and scalar multiplication, which I will call C1 up to C4, standing for compatibility of addition and scalar multiplication. And the first one is that if I have two elements, u and v, and I have a scalar, lambda, then if I add u to v, and then take the scalar multiplication, this is the same as first taking scalar multiplication lambda with u plus lambda with v. And C2, if I have a u and v, and I have two scalars, lambda and mu, then if I add lambda plus mu, so now you need to be careful. So this plus now is the plus of real numbers, and this plus here is the plus of this vector space. And these are two different things, so you need to be a little bit more careful here. So if I add these real numbers, I get a real number, and then I can take the scalar multiplication with u, and this should be the same as lambda u plus mu u. Yes, and C3 is if I have a vector u, and I again take two scalars, then real numbers, I can also multiply them. So if I multiply, or I will do it the other way around. So if I take the scalar multiplication of mu with u, this will give a vector, and then I can take the scalar multiplication with lambda. But this should be the same as lambda mu, and then scalar multiplication with u. And here this multiplication is just the multiplication of two real numbers, lambda and mu. And then the fourth property, which maybe sounds silly, but this is one of the conditions because this can be a really general setup here. So if I have a vector u on element in V, then 1 times u, so the real number 1 scalar multiplication with u, is just u. And these are the conditions for the definition of a vector space. And maybe if you read it the first time, this sounds silly, because for usual vectors in Rn, these conditions are quite easy to see. But what we want to do is we want to generalize this idea of Rn, and therefore we define a vector space to be a set with these addition and scalar multiplication, such that we have all these rules which we already know from Rn. And then everything we showed for Rn and for usual vectors if you look at the proofs, we always just use these properties, and therefore they will also be true for vector spaces in general. Okay, so now we want to prove some properties which follow from the definition of a vector space. So this will be proposition 1, 2. So let V be a vector space. And U is an element in V. So the first property is quite clear, which states that U plus N is U, where N is this neutral element in A3. And there the statement was that N plus U equals U. The second is that if N and another N, which I will denote by N tilde, if they both satisfy this condition A3, then they are equal. So in other words, if I have two elements which have this property that if I add them to something else, they don't do anything, then they are equal. So this means that this element N is unique. So there's always just one element N which satisfies this property. So in other words, there's just one zero vector. So the third condition, the third statement of proposition 1, 2 is that for a fixed U in V, so if I have two V's which satisfy this condition A4, meaning that they are both inverse of this U, so if they both satisfy A4, so this property was that if I add V to U, then I get the N, then they are also the same. Meaning that the inverse element of a fixed element U is always unique. And then the fourth statement is that if I have U and I add to this -1 times U, then this is this identity element N. Okay, so let's prove this. So this should all follow from the definition of a vector space. And the first is quite clear. So why is this true? Because we know that U plus N by property A2, so the addition is commutative, so it doesn't matter in which order we add them, is the same as N plus U. And then in the condition A3, N plus U is just U. The second one, N by the condition A3, is the same as N tilde plus N, because N tilde is an element which satisfies the condition A3, so it doesn't change anything if I add it to something. But by the first property 1 here, N plus something is just the something, so this is also N tilde. And the third, so we consider V tilde plus U plus V. So V tilde and V are now both elements satisfying the condition A4, meaning they are both the inverse of U. So this means if V is the inverse of U, then U plus V is just N. So this is V tilde plus N. And because N is the identity element, this is just V tilde. But by the condition A1, if I have a sum like this, it doesn't matter if I first add u and v, or if I first add v tilde and u. So this is the same as v tilde plus u plus v. But if v tilde also satisfies this condition A4, then this is also just the identity element n. So this is n plus v, and n plus v is v. So in other words, v equals v tilde. And the first one, I don't want to prove, but this is really maybe a nice exercise, because to prove this one, you need to use several properties of a vector space. So this is exercise for you. So what you need to show is that if you can show that 0 times u equals the identity element, so this is, if you can show this, you will see that you can also show this property here by using the property that u plus minus 1 u is 1 minus 1 u by C2. Okay. So this is the first proposition. And again, for usual vectors, these properties are trivial. So now there are some remarks for this proposition and in general for vector spaces. So the first one is that every time when you give a vector space, it's not enough to just give the set V, because a vector space is not just a set V, it's a set V together with these two operations, addition and scalar multiplication. So every time I ask you to give me a vector space, you need to give me three things: a set, addition, and scalar multiplication. And then due to this proposition here, this identity element n is unique, and therefore we will give it a name. So this n we will also write like 0, and you always need to be careful. So this 0 is now this identity element of v, and sometimes there will also be the real number 0, and you always need to be careful which one is which. So for example here, this 0 is the real number 0, and this is the 0 of the vector space. And the second is that here, due to the statement number 3, this inverse of an element is also unique, and therefore this v we will denote, we will also give it a name. So if u is in v and u plus v equals the identity or the 0, then we will denote this by minus u. And by proposition 1, 2, the last statement here, this is actually given by minus 1 times u. And then third statement is of this remark that this, if I have three elements in v, u, v, and w, then the sum u plus v plus w makes sense, because by this proposition A1, this we just say this is u plus v plus w, or u plus v plus w. So you not always need to use these brackets, because by this proposition A1, it's clear what we mean by this expression here. Okay, so now the last thing we want to do in the first part of the first lecture is to give an examples of some vector spaces. So this will be example number 2. Of course, the thing we did in Linear Algebra 1, if we take for v Rn, with the usual addition and scalar multiplication, so with the usual operations. This is one example of a vector space. And in this case, this identity element n, which we call 0, is just given by this 0 vector. And if I have a u given by a vector u1 up to un, then the inverse of u, which we denote by minus u, is just in each entry we take the negative of these numbers. And then the second example, which we discussed in example 1, is the set of all functions from R to R. And there we also said what f plus g means. If f and g are in this set, then by this we mean this is a function which is just f of x plus g of x, and the scalar multiplication of a function f evaluated at x is just lambda times f of x. And here this multiplication is just the multiplication of real numbers. And the identity element, in this case, the 0, is this function n, where n of x we defined to be 0 for all x. So this is the identity element, and the negative of a function, the inverse of a function, is just minus f of x. And now another example is what you studied in calculus. So, for example, there you studied infinite series, or sequences, infinite sequences, which I will denote by an, and n is a natural number greater or equal to 1. So for each natural number you had some number a, a2, a3, and so on. And you can also add two such sequences by just adding them at each place here. And you can also multiply them with a scalar. And this set I want to denote by capital I. So this is the set of all infinite sequences. And there are special sequences. For example, in calculus you studied for which an does the limit n goes to infinity make sense. And this will be an example of a subspace of these sequences, which we'll do in the next lesson. And the last example I want to give is example number 4, matrices. So we can take as a set V, we can take the set of m times n matrices. And for these we also define what it means to add two matrices and also to multiply a matrix with a scalar. So here again with usual operations. And there are much more examples, but these will be the main examples we will study in this course, especially these functions, which will play an important role, especially in the chapter of eigenvalues and eigenvectors. Okay, so that's all for the first part of the first lecture, and in the next part we will study subsets and subspaces.